Today we're going to be solving another system of ODEs, but we're going to be using the eigenvalue method, and we're using an example that has complex eigenvalues. So as always in these type of problems, we're going to let x be the vector with component entries x1 and x2. So then the derivative of this is the derivative of each one of these. And what we're doing here is we're just rewriting the system of ODEs in vector notation. So I go ahead and copy and paste that from the top. And if I do that, I get this. I then want to rewrite this as a matrix times the vector x1 and x2. So in order to make this work out, I'm going to need a 1, I'm going to need a -2, a 2, and a 1. And you can just go ahead and double check your work. Take the dot product of this and that. You should get that there. So now we have something of this form. We have the derivative of x times a matrix times the vector x. This should look familiar. If you go ahead and erase these vectors, pretend that p is just a constant and x is a variable. One of the ways you would solve this back in the day, not too long ago, is you would try the solution x is equal e to the lambda t. Well, if you go ahead and make p of a matrix and x vectors, you're not that far off. We want to try something similar, but you want a vector, so you're going to go ahead and put a vector there. Now, your goals are as the follows. You want to find, just like back in the day, what lambda is. You're going to do that first. And your second goal is to find what v is. How did we do that back in the day? Well, we took that equation and we plugged it in to that. So if you do that, and then so let's go ahead and do that just to make sure we understand this. So what is the derivative of x? It's v times lambda e to the lambda t. And on the right, we have p times v e to the lambda t. Well, the next step is to divide out by these quantities. And if you do that, you're going to get this equality. Well, we're trying to find what lambda is and v, and this should look familiar. These are eigenvectors and eigenvalues. That is the definition, provided the v is not 0. So you can go ahead and add this into the v that we want. We want a v that's not 0 and satisfies this equation. Well, how do we do that? Well, you set the determinant of p minus lambda is equal to 0. You actually want to find, so let me go ahead and multiply by the identity there. You want to find lambda such that the matrix on the inside is not invertible. All right, so now this is the point where we actually need what p really is. So let's go ahead and go up, scroll up. There is my p. I'm going to go ahead and copy that. And then I'm going to go ahead and paste it here. And then I'm going to go ahead and subtract my lambda times the identity. Well, let's go ahead and do that. We're going to get 1 minus lambda, -2, 2, 1 minus lambda. All right. Calculating the determinant, what we get is 1 minus lambda squared plus 4. We go ahead and multiply this out. We have a 1 minus 2 lambda plus lambda squared plus 4. And this is going to be lambda squared minus 2 lambda plus 5. So we want to factor this out. You're going to have to use the quadratic formula. So lambda is going to be -b plus or minus the square root of b squared minus 4 times AC, so we are multiplying by 5 divided by 2a. So we're going to get a 1 plus or minus Inside of here, you're going to have 4 minus 20, so you have negative 16. So then this reduces to I times 4 over 2. So then our eigenvalues are going to be 1 plus or minus I times 2. Cool. So we have found our lambdas. So going up to our goals, that is goal number 1. Awesome. So now we want goal number 2 is we want to find v such that this happens. Well, if you remember, what you do next is you go ahead and plug it into that. So this is the point where this method deviates from the real case when your lambdas are all real. When your lambdas are all real, you find eigenvectors for each one of them. But in this case, we're only going to be using one of them. We only care about one of them, and this single eigenvalue is going to give us the two necessary vectors that are linearly independent and also our solutions. So we want p minus lambda, which is 1 plus I2 times the identity. So then we go ahead and we need our p. So our p is this one here. So I'll go ahead and copy. And then I go ahead and paste it here. And then we want to subtract this quantity. All right, and if we do that, what we're going to get in the top left is the ones cancel, and you have minus I2. In the top right, you have a minus 2. In the bottom left, you have a 2. And in the bottom right, the ones cancel, and you have minus I2. So we're trying to figure out what v is. So what we need also in this is we need to multiply by a v times v, and in the top left, I'm going to set this to the vector 0. So I'm solving for a v that satisfies this equation. This v here is an eigenvector. So remember that an eigenvector, once you have the existence of one, you have an infinitely many of them. So it's a whole subspace. And this tells you when you row reduce your matrix, this one, you're going to have a free variable. And the only way you can have that is if you, after you row reduce it, you're going to get something in the bottom entries are 0, 0. And it's not that hard to see here that after a simple multiplication, you're going to get that. But this is always the case, so you don't need to waste your time trying to figure out how to row reduce it to that. Instead, you can just focus on what is at the top. So if you then want to solve this, this tells you that your v1 and v2, so this is my side work. Remember what v is. It is a vector with two entries, v1 and v2. So this tells you that v1 and v2 satisfies this equality is equal to 0. So we're going to let v2 be a free variable, so we're going to go ahead and just select 1. This then tells you that v1 is going to be, so you then add the 2 over, and then you divide out by minus I2. You want, sometimes this is going to look ugly, and you want to rewrite this so that you have I at the top. And the way you do that is by multiplying. So normally you're going to have a 0 here. And you're going to have something that is not 0. And that's what makes it sometimes difficult to bring the I to the top. But all you need to do is take the same number, and whatever sign is in front of the I, you just switch it to the opposite sign. So we have a minus, you make a positive. So you multiply this both to the top and the bottom. And after you do this, you're going to get the I at the top. And at the bottom, the i's are going to cancel, and you're just going to get a 2 at the bottom. So what we have is, my apologies, there's a small typo at the top. Instead of a 2, you should have a 4. So then this reduces to 2. So our solution that we tried was v times e to the lambda t. You go ahead and plug this in. At the top for v1, we have I times 2. At the bottom, you're going to have a 1. And then e to the eigenvalue. So we have to go up and remember what was our eigenvalue. It was this here. Copy that. Paste it. Put it at the top. Shrink it a little bit. Parentheses and a t. So our solution that we want it, even though this is a solution, we want it to have no imaginary parts at all. So then, what do? Do not worry. What we want to do is we want to write e using Euler's formula. So then we have e to the t. And in parentheses, we have cosine of 2t plus I, so times sine of 2t. You then want to go ahead and multiply this out. You want to bring it in and multiply it out. So then at the top, you're going to get I to e to the t cosine 2 to the t plus, so the i's this time are going to cancel, but I times I is going to give us a negative 1. And we're going to have a 2, we're going to have e to the t, and we're going to have sine, and in parentheses 2t. So then at the bottom, what we're going to have is just what's out here. We're just going to go ahead and copy and paste that there. Awesome. So now we want to separate this vector into two vectors. And in the entries of each one of these vectors, you don't want anything that is imaginary. You only want real parts. The only imaginary thing is going to be this I right there. So in the top entry, what we want is going to be, so I'll go ahead and do that in green here. We want this. So negative 2e to the t sine, and in parentheses 2t, we're actually plugging that into sine. And the imaginary part can go in the top right, which is 2e to the t cosine 2t. And then in the bottom entry, the real part of it is going to be e to the t cosine 2t. And in the bottom right, we're going to have e to the t sine of 2t. Awesome. This portion here is what we call the real part. We're going to go ahead and call that x1. The second portion here without the I, we're going to go ahead and call that x2. These are the solutions we were looking for. And notice that we did not use the second pair of the eigenvalue. We only used one of them. So then our general solution is going to be the following. It's going to be any linear combination of x1 plus c2 x2. And then always we can rewrite this as a matrix times the vector c1, c2. And for the first entries of column 1, you're just going to go ahead and put the entries of vector 1. And then for the second column, the entries of the second vector. So then our final matrix here, so I go ahead and take the entries of x1, copy, and then I go ahead and paste them here. Then I take the entries of my second vector, copy, paste them here. I created this 2 by 2 matrix, and on the right here, I'm going to have the vector C. Then our final answer is going to be, well, it depends how you want, what your final answer is. The general solution is what we have here. But this particular matrix here has a special name, which is called the fundamental matrix with a capital T. Awesome. Thank you.